For flight crews of turbojet aircraft taking off at or near maximum gross weight, or in the final stages of landing, a sudden change in wind speed and/or direction in a short time or distance along the aircraft's flight path can be catastrophic. At the National Center for Atmospheric Research in Boulder, Colorado, a program called the Joint Airport Weather Studies, and dubbed the JAWS Project, was established to investigate the magnitude of the wind shear threat in an aviation environment. Their early analysis led them to the conclusion that some types of wind shear, such as terrain-induced shears, nocturnal jet shears, sea breeze shears, and even the majority of warm and cold frontal shears were most often within the performance capabilities of aircraft, if anticipated by flight deck crews. So the JAWS research focused on those wind shears associated with convective storms, wind shears called microbursts, which seem to pose the greatest threat to aviation. A microburst is produced by the downdraft from a convective cell. As the vertical downflow nears the ground, it spreads out in all directions, causing a horizontal outflow and creating a situation where an aircraft attempting to penetrate the microburst would encounter the headwind, the downdraft, and the tailwind in a very short time and distance. At low altitude, on approach or departure, the resulting loss of airspeed can cause an accident. During the late spring and early summer of 1982, around Denver's Stapleton International Airport, the JAWS team brought together a collection of scientific equipment not previously used in this manner for wind shear research. Probably the most important of these tools was Doppler weather radar, which allowed the researchers to observe and record the directions and speeds of winds associated with convective storm cells moving through the area. Their findings were both impressive and surprising. Dr. John McCarthy, a pilot and meteorologist, was one of the directors of the project.
In our analysis of the JAWS results at Denver Airport, we found that there were many microbursts. It was very surprising to us, the number that we found. For example, we expected to see 10 to 20 microbursts in 90 days, and instead we saw 150. So there were many times more microbursts than we anticipated. We found some fascinating things. We found that microbursts can be incredibly intense, that the wind speed change when you fly through a microburst could be in excess of 100 knots in terms of wind speed. We know microbursts are very common here in Denver. We know from an experiment conducted in 1978 in the Chicago area that approximately half the number that occur at Denver occur at Chicago. That's still plenty of microbursts. We know from the accident statistics that microbursts occur anywhere where convection is occurring. We know that they occur in New York, St. Louis, Atlanta, Miami, New Orleans certainly, Tucson, and Salt Lake. We don't know all the places where they're occurring because we haven't set up all this fancy equipment. But when we have, or where planes have gotten into trouble, we have come to the conclusion that you can expect microbursts anywhere where there are convective cells, whether it's in the United States or anywhere in the world. One very interesting fact was that the average microburst during the JAWS project at Denver was 50 knots. And sad to say, that's stronger than the estimated value that brought down Pan Am 759 at New Orleans in the summer of 1982. So an average microburst is quite capable of destroying an airplane. In our careful look at our microburst statistics, we found that they don't last very long. They last 5 to 10 minutes. One of the most interesting things is that when a microburst first hits the ground, it's not as intense as it's going to be in the next 5 minutes. This is a very important finding because the first encounter, if it has just hit the ground, is half the intensity as it's going to be 5 minutes later. And several pilots have gotten into trouble by saying, hey, there's only a 20-knot shear, I can handle that, go into it and find out that it's a shear you can't fly through. Microbursts tend to occur in families. Not always, but oftentimes. We found that at Denver, that the presence of one microburst on some days was followed by the presence of many more microbursts, up to 15 on a given afternoon, often bunched into a 1 or 2 hour period. We conducted the JAWS project at Denver in 1982. In 1984, we were given the opportunity to test some of our concepts in short-term forecasting, detection, and warning of low-altitude wind shear back at Denver. For 45 days, we brought our research results to Denver in a real-time operational test to see if we could provide quantitative information to controllers and hence to pilots regarding the presence of wind shear. And we found that Doppler allowed us to come up with a 2 to 4 minute advanced warning of a microburst encounter by an airplane. And in fact, it was so successful that in one case we got a report back from a 737 pilot that said that the existence of that advisory saved his airplane from crashing. That's awful good news to people working in this kind of safety environment. My message to you as a pilot and as to you as a controller is to find ways of keeping aircraft out of microbursts. Avoid, avoid, avoid. That's the name of the game.
Awareness and avoidance of wind shear are important steps in being able to cope with it effectively. At many airports around the United States, the Federal Aviation Administration has installed low-level wind shear alert systems. At strategic points around the airport, remote anemometers measure wind speed and direction. They're usually located near the middle marker, but take into consideration terrain and other conditions unique to that airport. The peripheral wind information is continuously compared to readings of the center field anemometer, and if the differential exceeds a preset threshold, an alert appears in the tower cab. At 2 airports, New Orleans, Louisiana, and Denver, Colorado, the existing systems have been enhanced with additional detection stations to improve the system's ability to detect microburst wind shear. The low-level wind shear alert system is but one of the tools at your disposal. Remember, however, the absence of an alert does not preclude the presence of wind shear. If wind shear alerts are present, exercise extreme caution and look for other clues that may indicate the severity of the problem. For instance, we know that thunderstorms with heavy rain may include microburst wind shear. However, in some areas of the United States, you may encounter microbursts in much less severe conditions with little or no rain. These are called dry microbursts, and in these situations you may see precipitation trails or virga getting close to the ground but not actually hitting it. Below it you may see blowing dust. And if you have a situation like this, where you can actually see a ring of dust, it is a clear sign that there are extremely strong and localized winds. In other areas, you may see trees blowing out or flailing wildly, again a sign that extremely strong localized winds are present. Another source of wind shear information is pilot reports. Professional flight crews in particular are urged to make PIREPs. The recommended method for wind shear reporting is to state the loss or gain of airspeed, the altitude at which it occurred, your location, and type of aircraft. Since wind shear is such a dynamic phenomenon, PIREPs must both be made and disseminated as quickly as possible. There are also other potential clues as to the presence of wind shear. For instance, by examining the takeoff or landing path on your weather radar, although you cannot detect wind shear as such, you may see strong radar returns from thunderstorms which are sometimes associated with severe microbursts. Be aware, however, Microburst wind shear can also occur in weak echoes, or in fact, with no radar returns. This is Captain Gary Gore, a 727 pilot for United Airlines with nearly 13,000 hours. In the late spring of 1984, he was involved in a very serious microburst wind shear encounter at Denver's Stapleton International Airport. This is how he remembers that day.
Well, that morning, as I was driving to the airport, I happened to notice the mountains to the west were starting to pick up some lenticular cloud formations. And later on in dispatch, as I was reviewing the weather forecast, they indeed had forecast virga to be forming in the area later on that afternoon. Also a possibility of wind shears in the Denver area. When I walked out to the aircraft, I noticed the area was developing quite a few virga clouds. And I checked with my engineer to see what weather was as reported by the ATIS information. He said they reported gusty winds in the area, predominantly out of the west, and they were using runway 35 left at Denver, which is over 10,000-foot runway. And we went ahead with a normal pushback, and as we taxied around the east end of the building, found about 18 aircraft in front of us waiting for departure. The ground control told us to stay with them and get in the line, and when it became our turn to move over to the run-up area, the south end of 35 left, that would be the time they'd switch us over to the departure tower frequency. I elected to use 5 degrees of flap for our takeoff and told them to plan for a normal leaper, and when we got out to the runway, we would decide whether or not we would use the maximum leaper if conditions required it. There was fairly darkening lower level clouds coming in, and we could see some virga further up towards the north and the northwest of the airport. Nothing around the actual airport vicinity. We spotted some dust blowing about midfield point on the runway, and we discussed that in some length, and all recalled that they were doing some dirt moving and construction in that area, and that it indicated that there was fairly good wind blowing there, but nothing of any concern. About that time, I heard a Rocky Mountain Dash 7 call to the tower that it had a 20-knot loss on climb out. And as I looked out the front of the cockpit window, I could see the Dash 7 was about the midfield point where we'd spotted the dirt blowing. And he looked to be about 200 to 300 feet above the ground. I then proceeded to brief the rest of my flight crew that due to the look at the sky conditions and that, we would still be using the 5-degree flap takeoff, that we would use maximum EPR for the takeoff, and then the tower cleared us to follow next aircraft onto the runway. I turned on the color radar and observed and brought to the attention of the rest of the crew that we had a very strong cell with a red center, approximately 35 miles northeast of the airport. But since everything was moving from west to east, that it would not be a factor. We'd be turning to the northwest away from it anyway. At that point, we were lined up on the runway, and tower cleared us for takeoff. Said your north field wind is 270. It figures about approximately 8 knots. Your midfield wind is 270 at 20, gusting to something like 28, which correlated with the wind that was blowing across the runway and all that dirt at midfield point. And your south field wind is 260 at approximately 9. So I told the rest of the crew, I said, well, that looks okay. Set takeoff thrust and move the throttles up to the max EPR setting for the takeoff power. So we continue with the normal takeoff, and about the point where we've been observing the blowing dirt and where we thought the 20 gust and the 30-knot wind was located, the co-pilot called out. He says, got an airspeed hesitation here at 120 knots. And I looked down, and as soon as I looked down, the airspeed was starting to, he said, oh, disregard it. He says, airspeed's accelerating again. We continue with a normal takeoff roll and acceleration into VR. I started bringing the aircraft nose up, and about had about 9 to 10 degrees of body angle. When we just about reached V2, co-pilot called my attention again. He says, the airspeed's starting to decay. I glanced down to see the airspeed starting to move back towards VR. I reached over and I called for firewall power, and the co-pilot followed up on my push, and we had the throttles maximum forward. At that time, the flight engineer called out, "You've lost 20 knots." I looked down and observed the airspeed had actually decreased 20 knots from our V2 speed, and we're now starting back, it was about 10 knots below what our VR speed had been. I checked the rotation at about the 9-degree point we had, and I realized that we were committed and had to try and get the airplane off the ground, and I continued with the rotation, noting that the V speed was still about, we're about 2 to 4 knots below VR speed, but continue with the rotation. At about the point when we had an 18-degree body angle or so, all of a sudden the airspeed shot up at the same time that the airplane suddenly left the ground. My engineer was calling out our good body attitude, and airspeed was increasing, and at that point we had a normal climb out, except very bumpy and rocky. As we were about 9,500 feet, my engineer called out that he was having a problem to pressurize the aircraft. So then I advised the co-pilot, tell ATC that we cannot pressurize the aircraft, we'd like to return to Denver, and that we would be not requiring any assistance because it was just a pressurization problem. We then went ahead and had a normal approach and landing in Denver, and then taxied into the gate, shut the aircraft down, and went through the shutdown procedure. At about that time, I noticed quite a few of the ramp people coming out and scurrying over to look at towards the back of the aircraft. My co-pilot asked, would it be okay if he went back there to see what everybody was going back to look at? And I said, yeah, go ahead. And I said, I'll help the engineer write up the problem with the pressurization. But shortly after that, my co-pilot came back and he said, I think we found the pressurization problem. And I said, oh, how come so fast? He says, well, it seems we got a piece of red and white antenna sticking in the belly of the airplane.
The antenna referred to by Captain Gore was located nearly 1,200 feet beyond the end of the runway and was broken off only 13 feet above the ground, dramatic proof of the potentially devastating consequences of a microburst encounter. Like Captain Gore's experience, many times the warning signs may not be absolute, so be alert to the sum total of all indicators. On takeoff or landing, if you do suspect wind shear, consider your runway selection or a short delay until conditions are more favorable. If you do make a go decision, either to take off or land, consider the options available to increase the performance of your airplane, such as your flap setting and your speed margin. If you do find yourself in a severe low-altitude wind shear during takeoff or landing, anticipate increased performance as you enter the headwind portion of the shear, followed by suddenly decreasing performance as you transition into the downdraft and tailwind segments of the shear. In this situation, you must respond quickly and correctly to avoid an accident. Increased thrust may be required all the way to full forward throttles, and trading speed for altitude by increasing your pitch attitude as necessary up to stick shaker speed may allow you to maintain or establish a positive flight path. Now, let's sum things up. The relative rarity of severe low-level wind shear encounters may in effect increase their potential as a hazard. Be prepared when you're operating in areas where the potential for wind shear exists. Be alert not only to low-level wind shear alerts from ATC, but also to PIREPs from other flights. And remember, you are an important part of this information process. If you suspect wind shear, report it. Although your encounter may have been minor, the changing nature of the phenomenon could make that encounter critical for a subsequent flight. Review your operating procedures on a regular basis and know the performance limits of your aircraft So if you find yourself in an emergency situation, you can respond promptly and correctly. Remember, there have been documented cases of wind shear which no aircraft has the capability to successfully traverse.